Okay, so the last thing we want to look at is take the stuff we've been doing with growth rates and which function grows faster than another. And we want to take this idea now and kind of just formalize it in a little bit of a list, kind of a ranking for how quickly functions grow. So we first introduce a notation as double less than means that the second function on the right grows faster than the one on the left. So F is slower than G. F's growth rate is slower than G. These are, of course, all dealing with things that are growing towards infinity. So when we talk about this, we're talking about as we go out to infinity. So we introduce some parameters here, P, Q, R, and S. Let those all be greater than 0. Be real numbers. And be greater than 1. Be a real number. Now, we know nothing about the relationship as far as what's bigger, P, Q, R, S. That doesn't matter. That doesn't matter. These are just positive numbers. Okay, so the first things first. Any ln, no matter how big the power is, of x, will grow slower than any positive power of x. But that positive power of x will grow slower than x to the p ln raised to some power. Okay, so if you have ln raised to a power multiplied onto an x to the p, then it will grow. That will grow faster. But no matter how small the power that you include with it, as long as it's bigger than p on x, that will still outperform an x with an ln. Right? In other words, ln is slower than any power of x, no matter how small it is, as long as it's positive. But adding an ln onto the x does get you bigger than an x to the p. Does get you bigger than an x to the p. But even if you have an x to the 1/100th, or an x to the 0.01, included with x, and you might have an ln to the millionth power, that will still grow slower than having that extra little 0.01 x on there. And of course, every polynomial power grows slower than an exponential function. Okay, but every exponential function is outperformed by that super exponential x to the x. Is outperformed by that super exponential x to the x. We're actually going to add on to this list, and it will be kind of important later on. For now, it's just kind of an observation. Any ones that we need to compare, we're actually going to compare by using our limit properties and taking the limits. But later on, having this as kind of a checklist to compare these functions. In fact, we're going to be looking at later on at fractions involving different combinations of these functions and some other functions. Then this ranking list will be useful then. Just to kind of explain a little more about this first part here, let me just show you some examples. For example, ln of x is outperformed by x, any power of x, so like x cubed. But as soon as you have an ln with the x cubed, ln, although it's very slow, is still enough to outperform the x cubed. However, that would get performed by even just having a simple thing like 10th root of x, or x to the 0.1 power. That would be enough to outperform the ln, even if you had the ln raised to some big power like ln to the fourth. Right? It would not matter. It would not matter. Even that tiny little x to the 1/10 power is enough to overwhelm the ln. Of course, we see that here. Any power of x will outperform any power of ln. Okay. So one final thing on growth rates, if you're doing any kind of computer science, is the same idea in computer science. When you talk about algorithms, they talk about algorithm complexity, how complicated is an algorithm. And of course, the holy grail of algorithm complexity is for it to be growing logarithmically. That's the one you want. That grows the slowest. That means the more things you add on, the time it takes grows logarithmically. Usually it's log base 2. That, of course, grows slower than n log base 2 of n. As in computers, we are dealing with things in binary. But that grows slower than a square algorithm. Right? So n log base 2n is slower than n log n, but that's slower than, or that's n squared is faster than that. So ideally, you want this in computer science, what's called kind of like the best. If your algorithm, as you increase the number of things, if it's scaling at a factor of log base 2 of n or log of n, then that's what you want. N log n's faster or slower, and it's going to have more steps, but it's still better than an n squared algorithm. Of course, n is linear. Kind of could, I guess, have put that one in there as well to kind of round that out. But this is something, and again, if you're not in computer science and this is not something you've dealt with, don't worry about this. I'm just throwing that out there for those that have had that background in computer science. You've seen this kind of thing. This is just this taking what we've just talked about and expressing it in computer science terms. Okay, so you'll sometimes talk about that in computer science. But again, if that's nothing that relates to you, then don't worry about it. It's just, again, an extension of this idea with growth rates.